Before we begin, I want you to do something simple but important. Watch this video all the way to the end, because the final idea might completely change how you think about the universe, and especially about what happens when something falls into a black hole. Imagine this. You're looking into the night sky, and everything you see, every star, every planet, every galaxy, is only a tiny fraction of what actually exists. Most of the universe is invisible. It's made of something we call dark matter. We can't see it, we can't touch it, but we know it's there because of how it pulls on everything else. Now here's the question that sounds simple, but gets incredibly deep. What happens when that invisible stuff falls into a black hole? Because black holes don't just swallow light, they swallow everything. Or at least, that's what we think. Let's start with what we do know. A black hole is formed when a massive star collapses under its own gravity, creating a region in space where gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. Inside that boundary, the rules, as we know them, begin to break down. Physics gets weird. Time behaves differently. Space itself is distorted. Now think about dark matter. Unlike normal matter, dark matter doesn't interact with light. It doesn't absorb it, reflect it, or emit it. That's why it's invisible. But it does have mass, and because of that, it feels gravity. And that's the key connection. Gravity is the bridge between black holes and dark matter. So if dark matter feels gravity, then a black hole should be able to pull it in just like it pulls in gas, dust, stars, and even entire galaxies over time. But here's where things start to get strange. Dark matter doesn't behave like normal matter. It doesn't collide with itself in the same way. It doesn't clump together into dense objects like stars or planets. Instead, it forms these vast, diffuse halos around galaxies. So when dark matter moves near a black hole, it doesn't necessarily spiral in and form an accretion disk like normal matter would. It might just pass by, barely interacting, unless it gets very close. But if it does get close enough, if it crosses that event horizon, then whatever happens to normal matter should, in theory, happen to dark matter too. It becomes part of the black hole. Now here's where things get even more interesting. What does it mean to become part of a black hole? From the outside, all we can measure about a black hole is its mass, its spin, and its charge. That's it. This idea is sometimes summarized as black holes have no hair, meaning they don't retain detailed information about what fell into them. So if dark matter falls in, its unique properties might be lost, at least from our perspective. All we would see is that the black hole's mass has increased slightly. It wouldn't matter whether it swallowed a star, a cloud of gas, or a clump of dark matter. The result looks the same. But that raises a deeper question. Is the information truly lost, or is it hidden in a way we don't yet understand? This connects to one of the biggest mysteries in physics, the information paradox. According to quantum mechanics, information can't be destroyed, but black holes seem to erase it. So what happens to the information contained in dark matter when it falls in? Is it encoded somehow on the surface of the event horizon? Is it preserved in a way we can't yet detect? Scientists are still trying to figure that out. Now let's take this one step further, because this is where it gets really messy. Some theories suggest that dark matter might not be made of particles like anything we've ever seen. It could be something entirely different. If that's true, then its interaction with black holes might reveal new physics. There are even ideas that certain types of dark matter could accumulate around black holes in unique ways, forming dense spikes that could affect how black holes grow. In fact, some researchers think that by studying black holes, we might indirectly learn what dark matter actually is. Because even though we can't see dark matter itself, we might see its effects on the behavior of black holes, on their growth, on the way they merge, and on the gravitational waves they produce. And speaking of gravitational waves, this is another fascinating angle. When black holes collide, they send ripples through space-time. If dark matter is involved in those systems, it might subtly change those signals. Detecting those changes could give us clues about the nature of dark matter. So in a way, black holes might not just be destroyers. They might be laboratories, extreme environments where the deepest laws of physics are tested. Now pause for a second and think about how incredible this is. We're talking about something we can't see, falling into something we also can't see, and yet we're still trying to understand what happens using nothing but physics, math, and observation. And if you're enjoying this so far, this is a great moment to like the video, subscribe, and hit that notification bell, because we're just getting into the most fascinating part. Let's talk about the inside of a black hole, or at least what we think might be happening. According to general relativity, everything that falls into a black hole is crushed into a point of infinite density called a singularity. But many physicists believe that this picture is incomplete. When you combine gravity with quantum mechanics, the idea of a singularity might break down. So what happens instead? We don't know for sure. There are theories about quantum cores, about fuzzballs, about exotic states of matter. If dark matter falls into a black hole, it might contribute to whatever this internal structure really is. But without a complete theory of quantum gravity, we're essentially guessing. There's also the question of Hawking radiation. Black holes aren't completely black. Over incredibly long timescales, they can slowly evaporate by emitting radiation. If that's true, then eventually, everything that fell into a black hole, including dark matter, might come back out in some form. But here's the catch. Hawking radiation appears to be random. It doesn't seem to carry clear information about what went in. So again, we're faced with the same mystery. Is the information gone or just scrambled beyond recognition? Now let's zoom out again. Dark matter makes up about 85% of all matter in the universe. Black holes are scattered throughout galaxies, from stellar mass black holes to supermassive ones at the centers of galaxies. That means interactions between dark matter and black holes are happening all the time, everywhere in the universe. And yet, we still don't fully understand either of them. That's what makes this question so powerful. It sits right at the intersection of two of the biggest mysteries in modern physics. What is dark matter, and what really happens inside a black hole? By studying one, we might unlock the secrets of the other. Now imagine the future. New telescopes, more sensitive detectors, better models. We might start to see patterns we couldn't see before. We might detect subtle signals that reveal how dark matter behaves near black holes. And that could lead to breakthroughs that change our understanding of the universe. Because sometimes, the biggest discoveries come from asking questions that seem impossible to answer. And this is one of those questions. Before we wrap up, I want you to go down into the comments and tell me this. What do you think happens inside a black hole? Do you think information is truly lost, or is it somehow preserved? I'm really curious to hear your thoughts. And if you found this video fascinating and want to explore more mind-bending ideas about space, physics, and the universe, make sure to like the video, subscribe, and turn on the notification bell so you don't miss what's coming next. Thanks so much for watching all the way to the end. I really appreciate you spending your time here with me, and I hope you learned something new or saw the universe from a different perspective. See you in the next video.